Hi there, welcome to lecture 24 of Fox, and today is an exciting day because we are going to introduce our first very simple computing machine. So it's an example of a model of computing, and so we're really delving into the theory of computing. And this computing machine, this model of computing goes by many names: Deterministic Finite Automata, Finite State Machines, and for short, we will just call them automata. And the basic idea is captured by this cartoon from this very famous game, Super Mario Brothers, where you can think of Mario himself as an automaton, as a finite state machine. And Mario eats things, mushrooms, fire things, feathers, blah, 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 blah. Okay. And this sequence of things that Mario eats can be considered as an input sequence. And as Mario eats things, Mario changes states to Fire Mario, Super Mario, Cape Mario, and so on. So Mario is an example of a finite state machine, an automaton. Okay, so we're going to be discussing that kind of formally today, our first model of computing. So get excited and stay tuned. Okay, quick review of the main ideas from last time. Okay, so the main idea from last time was, how do we define a computing problem? And we said we're going to focus on decision problems, and that is a definition of a computing problem that has withstood the test of time. It's quite general. You can solve optimization problems, search problems, and so on and so forth. You can essentially by posing them as a sequence of decision problems. Okay, but now once we focus on a decision problem, that decision problem has to solve this decision problem, you take an input and you must say yes or no. That's what it means to be a decision problem. Decide yes or no something. Okay, and so then there are the inputs for which the answer is yes. We call this the yes set, and that is defined as a language. That's an example of a language. So we introduce the concept of a language, and essentially any set of finite binary strings can be used to define a computing problem. Okay, and then we can ask, how hard is the problem? Okay, and that translates to how complex is the language? How complex is the yes set associated with the problem? And what does it mean to be a complex yes set? It means it's not easy to test membership in the yes set. So if we have the yes set corresponding to primes, how easy is it to test membership in this set? Okay, that if it's hard to test membership in this set, then that suggests that the problem is complex. Okay. If it's impossible to test membership in the set, that suggests the problem is impossible. Okay. So this allows us to sort of formally define up what is a computing problem as a language and formally address the issue of how hard is the computing problem by looking at the complexity of the language. Okay. And then, we said that problems can be harder in sort of two ways. Well, the first way is, I have a computing machine like this Mario, this finite state automaton, this finite state machine that changes state. So I have a simple computing machine, and we don't really know formally what that is yet. Okay, but I have a computing machine, and I need to make it bigger and bigger, or faster and faster, in order to solve the problem. Okay, that means I need more resources. That's one kind of harder. I need more resources to solve the problem. And in an algorithms course, you study how to solve problems using the minimum amount of resources, where resources could be memory or runtime, and so on and so forth. Okay, but another way in which a problem can be harder is, you gave me a computing machine, and no matter how much resources you give me with this computing machine, I'm not going to be able to solve this problem. That's a different kind of hard. You can't give me more and more resources and expect that I should be able to solve the problem. And that kind of hard suggests that, okay, if a problem is that kind of hard, then we need a different kind of machine, a machine with superior capabilities. Okay? And that's the focus. This second question is the focus of this course. So we've now got our first model of computing, this finite state machine, which we're going to describe today. Okay, and we will see that we can solve lots of great problems, and if you give me more resources, I can solve harder and harder problems. But then we will eventually confront a situation where we will find some problems that no matter how many resources you give me, I won't be able to solve the problem. And that leads us to an interesting question. Well, is there a deficiency in this machine? Is there some other superior kind of machine? That's what we're going to study. Okay? And so, plan for today, we will introduce the finite automaton, the deterministic finite automaton. Deterministic is qualifying the fact that there are other kinds of finite automatons, specifically non-deterministic, kind of random, using randomness. Remember probability? Okay. So non-deterministic has to do with sort of uncertain direct ways in which the computing might occur. Okay. So we're going to focus on the deterministic version of a finite automaton, and we'll look at what problems we can solve, and then we'll ask the question, can we solve all problems? And if not, is there a superior machine that we might be interested in? Okay, so let's go to the board. Let's start with a sort of a quick review / practice of languages, in particular regular expressions, because the regular expressions are going to be relevant today. since languages are so important in the theory of computing, they define computing problems, let's have a quick review, and we'll have a quick sort of practice session with regular expressions, because those are very important in computer science, and then we'll talk about, finite automata, this very simple model of computing that can solve problems, okay, and we'll investigate their capabilities. So, languages, review. So a language L is a collection of finite strings. Okay, so collection of finite strings. Okay, and then you might ask, strings, what are the characters in these strings? So we typically call that the alphabet. Okay, now we're sort of being a little more formal than we were last time. So we typically call that the alphabet sigma. Okay, in our case, the default alphabet is just 0 and 1, so binary strings. So these are collections of finite binary strings. For the better part of this course, that's all we're going to care about, finite binary strings. Okay, and now I'm going to list a bunch of regular expressions. Okay, and you're going to have to figure out what those, what that regular expression represents as a collection of strings, and then I'll go in and work it out. Okay, so see if you can work it out before me. Okay, so here are a bunch of regular expressions. Okay, so sigma star. So this is the clean star. Okay, what is that? Okay, sigma star. Okay, where sigma is, it's an alphabet, so it's itself a language. Okay, but it's just consisting of my characters 0 and 1. Okay, what about this guy? The empty string 0 concatenated with the empty string 1. Okay, what is that? Okay, 0 star concatenated with 1 concatenated with 0 star. What is that? So these are all regular expressions. So now this is the clean star. This is illustrating concatenation. This is clean star plus concatenation. Okay, where this is the string 1. Okay, sigma star concatenated with 1 concatenated with sigma star. What is that? So clean star and concatenation. Okay. Most of the time when we talk about regular expressions, most of the operations that are used are the clean star concatenation. We sometimes use union, okay, but most of the operations are clean star and concatenation. What about this guy? 0 star concatenated with 0, 1 concatenated with 1 star. What is that guy? Okay, and then here's an interesting guy. Sigma concatenated with sigma. Okay, now take the clean star of that. Okay, what is this language? These are all regular expressions. We'll come and work them out. And then sigma concatenated with itself 3 times, so sigma cubed. This we could call sigma squared. So sigma cubed, now you take the clean star of that. What is this language? Okay, so lots of languages here. Okay, so I'll give you guys a few seconds, pause the video, and try to figure out in sort of English, okay, what these regular expressions represent as a set of strings. So I'll pause 1, 2, 3, 4, 5. Okay, now let's solve this problem. Okay, or these problems. Okay, so sigma star. Okay, this is the collection of strings that are formed by any number of concatenations of 0, 1. So you can start with the empty string, 0 concatenations. Then, just take each of the characters, 0, 1. Then concatenate, take 2 characters from here and concatenate. So then you get either 0, 0. If both of them are 0, you get 0, 1, 1, 0, 1, 1. And then 3 characters, 0, 0, 0, and so on. You will soon convince yourself that sigma, the alphabet star, is basically all the finite strings that can be formed using those characters. So this is all finite binary strings. Okay, I hope you got that. If you did, fantastic. Okay, this is the concatenation of 2 finite languages. So that you have to just explicitly solve it. So epsilon concatenated with epsilon is epsilon. 0 epsilon is 0. Epsilon 1 is 1. And then 0, 1 is 0, 1. So you take a string from here, concatenate it, followed by a string from here, and those are all the strings you can get. Okay, what is this guy? Well, let's look at it. So 0 star is any number of zeros, including 0 zeros, followed by a 1, followed by any number of zeros. Okay, that's what 0 star means. Okay, well, that's just any string which has exactly 1, 1. Strings with exactly 1, 1. Okay, hope you got that. Okay, now let's look at this guy. It's very similar to this. Okay, but this is sigma star. Now we know that sigma star is any string, any finite string, followed by 1, followed by any finite string. So these are all the strings with at least one 1, because sigma star could be empty, So these are all strings with at least one 1. Strings with at least one 1. Okay, let's look at this guy. Well, some number of zeros, possibly 0 zeros. So some number of zeros followed by 0, 1, followed by some number of 1s. Okay, but this 0 here, when you concatenate it with 0 star, makes it, a non-empty string of zeros. And this makes this 1 followed by 1 star makes it a non-empty string of 1s. Okay, so this guy here is a string of zeros, cannot be empty. This guy here is a string of 1s. So what we have here is a strings with, zeros followed by 1s. And in both cases, you cannot have 0 zeros and you cannot have 1 0. So to be technically correct, strings with at least 1 0 followed by strings with at least 1 1 and then only 1s. Okay, this is interesting. Sigma sigma. So sigma sigma. Okay, this is sigma. So sigma sigma is all binary strings of length 2. Okay. Now you take star. So you're concatenating all binary strings of length, all concatenations of the binary strings of length 2. Okay, it could be empty, okay, but after the empty string, you're concatenating strings of length 2. So you have to get an even string, and in fact you get all the even strings. Strings of even length, including 0, length 0. So this is very similar. Here, sigma cubed. So what is sigma squared? Sigma squared is just 0, 0, 0, 1, 1, 0, 1, 1. And now you take the star of this, you get the even string. Sigma cubed is exactly all the binary strings of length 3. And you take all possible concatenations of those, you get strings of length equal to multiple of 3. Okay. And so there. And if you got all of these, fantastic. Boy, you are an expert in regular expressions. Okay. And if you didn't, then, sit back and sort of think about these and just revel in the beauty and the power of regular expressions. So regular expressions, so these are very compact expressions that represents sort of non-trivial sets of strings. Okay. So now let's introduce. So that's a quick review of languages and regular expressions. Why did I focus on regular expressions? Because regular expressions are going to be relevant to what we're discussing today, which is finite automata. Deterministic finite automata, we'll just say automatons or automata. Okay, so let's erase, talk about automata. Okay, automata. Basically finite state machines. State machines. And everything here is sort of relevant. Okay. State machine means it's fundamentally composed of states. Okay. And finite means it has a finite number of states. And that's very relevant because we like to build these things. Okay. You can't build things with infinite number of states. Okay. So in your mind, okay, think of a state machine as some kind of a central processing unit. Okay. And it has states. Q0, Q1, Q2, Q3, Q4, Q5, Q6, Q7. So in this example, I've drawn the central processing unit, my state machine with 7 states. And you can think of some kind of a needle, that can rotate around and sort of indicate what state am I in. So at any time I can sort of, ping my own state. I can say, what's my state? Okay, so and I just look at where's the needle pointing. So the needle goes round and round, depending on, what stimuli I experience. And so where is the stimulus coming from? That's the input. Okay, so you can think that there's an input, and now, what's the input? Remember, we've formulated a computing problem as a language, and to solve the problem, the task is I give you an input string W, okay, and then you have to say yes or no, is it in the language? So, since we're building a machine, a very simple machine that solves computing problems, i.e. tests for membership in a language, the natural input is a string. In our case, we are focusing on binary strings. So the input is a string W, which is composed of 1s and 0s and so 1, 1, 0, 1, 1, 1, 0, 0, just an example string. Okay. And so, if there's going to be an input to this central processing unit, then it must have some kind of a read head, okay, which can read the input. And so the idea here is that the read head will start somewhere, and typically we will say that it starts at the left, okay, and then it chomps up the first bit of the input, processes it. What does it mean to process it? Flips around and bumbles around and changes state like Mario. Okay. Then it chomps the next input and chomps the next input. And each time it chomps an input, it processes it, moves around, and then says, this is my current state. Okay. And it goes through the whole input, and then when it comes to the end, it's done, because there's nothing more to sort of, there's nothing more to do there. There are no more inputs to chomp up, to process. Okay. And so when it's done, it's in some state, in this case, for example, Q1. And then when it's done, chomping up all the inputs, so we sort of, need some implicit way of telling the machine you're done with your input, so it tries to chomp and sees dirt. Okay. And at the end of chomping the input up, it has to output, yes or no. Okay, so it has to say what's my answer? Is my answer yes or no? And if the machine works, in other words, if it solves the problem, it'll only say yes when the string W is in your language, is in your problem, and it'll only say no when your string W is not in your language. Okay, so that's what it means to solve the problem. Now, okay, this is a nice picture to have, a central processing unit and so on and so forth. Okay, but we now need a more formal way to represent this machine. In particular, what does it mean to move around? Okay. Now we've understood how it processes the string. It just goes one by one through each bit, and we're going to leave the physical, the implementation details of that out of the theoretical discussion. Okay, so it processes the input string from left to right, one bit at a time, and when it comes to the end, it stops and says yes or no. So that part, we're going to take for granted, and we're going to focus on what's going on inside my machine, what's going on inside my central processing unit. Okay, so here's what's going on inside. Okay. Inside, it basically needs to have a set of instructions that tell it what to do for every bit that it chomps up, for every bit that it sees. Okay, and so there are a couple of things that we need to discuss. So the first thing is what are the states? The states. Okay. Second thing, what state do I start in? Because you gotta I need to know where to start myself, so I'm born. Okay, what state am I born in? What state do I start in? What are the states? What state do I start in? Okay. What are my instructions? So how do I move around? How do I change states depending on the bits that I see? Okay. How do I change states? And then, once I'm done with the input string, once there are no more bits, okay, how do I decide yes or no? How do I decide yes or no? So let's discuss all of these things. Okay, so in this example, what are the states? Okay, there are 7 states, but let's take a much simpler example to illustrate. So let's imagine a finite state machine with 3 states. So I have a state. Typically, we start labeling the states Q0, Q1, Q2. Now you can label the states any way you want. Okay, and in general, when we build these machines, we try to label the states to sort of indicate what the state means, and that will become clear as we do more and more examples. Okay, but the most abstract way to label states, the sort of simplest way to label states, is just like we're labeling a graph. We label the vertices v1, v2, v3 up to vn. So we have states q0, q1, q2. Okay, and let us agree that the state labeled Q0 will typically always be the start state. That's why we say 0 for that. Okay, at time 0, at bit 0, I'm in state Q0. Now, normally we will indicate that with some kind of an arrow, okay, to indicate that that's where you start. So these are my states. Okay, so I've told you the states and what state I start in. Now, how do I change states? Now, the most beautiful way to represent the mechanics of changing states, what you can think of as what are my machine instructions? What's the instruction set that I'm going to operate with respect to? What's the instruction set that I'm going to use? Okay, the most beautiful way of representing the machine's instruction set is using a directed graph. Okay, so we put these states as vertices in a graph, Q0, Q1, Q2. Okay. And now what I need to do is I need to tell the machine, how to change state. So which state you go into depending on what state you're in and what bit did you read. Okay, what bit did you chomp? Okay, so this is the start state. This is the, state 1, state 2, and we'll indicate the start state with an arrow. Okay, and then, what I'll say is that if you see a 0, so I'll indicate that with an arrow from the start state. So when you start and if you see a 0, go to state Q1. Okay, if you see a 1, please go to state Q2. Okay. Okay, and now if I wanted to be very formal about this, I would actually write out the instruction set, because we can't really represent pictures in a computer, but an instruction set that's well written out we can. So instruction set, or we can call it machine instructions. Okay, so what does this? So each arrow here corresponds to 2 instructions. What this says is, if you're in state Q0, okay, and you see the bit 0. Then please transition to state Q1. Okay? So a machine instruction is just a triple. What's your current state? What did you see? Where do you go? Okay, so here, what's this instruction? 1, 2, 3, do it. Okay, and now I'm going to tell you, it's the instruction, if you're in state Q0 and you see a 1, then transition to Q2. Okay, and so I'm going to now draw all the instructions, because I have to tell the machine what to do in every state and for every bit that it could see. So in state 1, if you see 0, please continue to stay in state 0. If you see a 1, transition to state Q2. Okay. And in state Q2, if you see a 0, please transition back to Q2. If you also see a 1, please transition back to state Q2. So to sort of avoid having to rewrite that same arrow twice, I will put a 0 and a 1 as the labels of this arrow. So that means that, if you see a 0 or a 1, you stay in Q2. Okay, so let's write out all those instructions. So here, if you're in Q1 and you see a 0, stay in Q1. If you're in Q1 and you see a 1, move to Q2. If you're in Q2, okay, and you see a 0, stay in Q2. If you're in Q2 and you see a 1, stay in Q2. There. Okay. So, how do I change states? You can specify machine instructions. If you don't want to draw stuff. Okay, but this is ugly. We don't know what's going on here. But when we look at this, look at how beautiful it is. So we can specify the mechanics of how my finite state machine is operating using a directed graph of this form. We call this, the state transition diagram. Machine instructions. Okay? State transition diagram. State transition diagram or graph. Graph for the obvious reason that it is indeed a directed graph. One of the most beautiful applications of directed graphs is to sort of represent models of computing. Okay. Now, okay, let me tell you, how do I change state? So first, in order to specify how you change states, I have to specify your instruction set. And now I'm going to now tell you how we use this instruction set in order to change states. So the process is very simple. Step 1, Okay, so how does the machine operate? Machine operating instructions. Okay. Start in the start state. Start in the start state. Okay. Q0. Okay. Now, process bits from your string one by one. 2. Process bits from the string, input string, one by one. Okay, so you'll process input bits, one by one. Okay, and for each input bit, follow the corresponding instruction depending on your current state, okay, and what the bit is. For each input bit, for each input bit, follow the instruction for the current state and bit. Okay. And now, when you're done with bits, when no more bits, when there are no more bits, you've arrived at your final state, at your resting state. So this means that you are at your resting state. Okay. So you're done with the computation. Now all you need to do is output yes or no. Okay. And so what we're going to do is we're going to ask you, when you specify states, to also tell me which states are yes states and which states are no states. That's the final ingredient in the automaton, which is to tell me how to say yes or no. So determine, say yes, if your resting state is a yes state, and no if the resting state is a no state. Okay. So when I specify the states, I need to tell you what are the yes states and what are the no states. So we need a sort of a notation for that. So, now if we were in black and white, the notation would be you place sort of a double circle around the yes state. So this is the yes state. That indicates the yes state. Okay, in this particular example, the starting state is a no state, and the state Q2 is a no state. Okay. Now, just once, I will show you what it looks like in the book with color. What we do, just to emphasize that this is a yes state, is we also color it green to indicate, wow, this is a yes state. Look at my beautiful coloring abilities, green. Put a little bit of nice, green. Okay. And so if I do that in this picture as well, so now in black and white, and the simplest way to do it is to just say, okay, here, double circle. That indicates that it's a yes state, but let's get all fancy and color beautifully. We need to have time lapse so that you can see time lapse coloring. And then you'll learn how to do coloring of finite automaton states. Look at how beautiful it is, soothing. Okay, there. Okay, so let's do an example. Okay, let's do a bunch of examples. So let's start with this machine and let's see what does it do with the input string 0, 1, 0. Okay. So now, one way to sort of represent the start of the computation, and so this is sometimes called the state of the machine. Okay, so we have the machine. Okay, so the machine is starting in state Q0. So we have the machine starts in state Q0. Okay. Starts in state Q0, and I'll put a line here to just indicate that that's its state, and a read head. So it has a read head. Okay, so the read head, where is the read head? Is at 0. Okay, and then the rest of the string is also still there. Okay, so this is one way to represent sort of the configuration of the machine. Okay, and now let's follow the instructions. Okay, so what's the first thing it does? It reads in the 0. So it reads in the 0 from state Q0. It reads in the 0 and goes to Q1. So we would say that, under the influence of the machine, okay, so let's give this guy a name. Let's call it M. Okay, so under the influence of the machine, this configuration, after it chomps up 0, okay, will be state Q1. Okay, so it goes from 0, it sees the 0, goes from Q0 to Q1. Okay, and it's processed the 0, and so now its read head is ready to process the 1. And then there's the bit 0 afterwards. Okay, so that's just a little bit of notation that allows us to keep track of what the machine is doing. Start in state Q0, ready to process bit 0. Okay, and by the way, there are some other bits remaining. Okay, so we processed bit 0, so that means that it's now on the left of the read head. Okay, so the read head has moved one step to the right. So I'm ready to process bit 1, and I'm in state Q1. Okay, so I'm in state Q1, I process bit 1, I go to state Q2. So under the influence of the machine, I go to state Q2. I've processed 0 and 1, and I'm now ready to read bit 0, and there's nothing after that, okay? And then under the influence of the machine, I'm in state Q2, I process the 0, I stay in state Q2, so I stay in state Q2, okay? And now I've processed 0, 1, 0, and my read head is positioned at a spot where there are no more bits. I'm done. Okay? And then I look, Q2 is not a green state, it's not an accept state. Now usually we won't have the green, we'll just have the double circle. It's not an accept state, so I say no. Okay, so this gives me no. Okay, so pop quizzes, exercises. Okay, give the trace. So that we call this the trace of the computation. Give the trace for the following inputs: epsilon 0, 0, 0, 0, 1, 1. Okay, pause the video, 1, 2, 3, 4, 5. Okay, now if you're coming back, okay, you should have said epsilon is, the answer is no. Okay, so this is no, no, yes, no. Okay, now I'm going to give you a harder exercise. Okay, so I'm going to show you, so at any time we can tell you what the configuration of the machine is, and you can continue the computation. For example, here the configuration is, I'm in state Q2, and I'm going to see 0, 1, and then I've already processed 0, 1, and what's remaining is 0 and nothing else, and I'm currently reading 0. So I'm going to give you some configurations, and you are supposed to continue the computation and tell me yes or no. So here's the configuration. Q0. Okay, you've processed some bits, and now here's the twist. I'm not going to tell you what you've processed, but your configuration is 0, 0, 0. Okay, so you have remaining 0, 0, 0. And then you're in, let's say Q0, Q1, and you've processed some bits, and I'm not going to tell you what you've processed, and you're next, you're positioned to read 0, 1, 0. So these are interesting. You say, well, but these configurations are there. You can think of them as partial configurations. Okay, and pause the video and see whether you can identify what's the final answer, yes or no. In the meanwhile, I'm going to erase the machine's operating instructions. Okay, and you pause the video 1, 2, 3, 4, 5, and you're coming back, and here you should have said yes. Here, you should have said no. Okay, and this is a very important property that I'm illustrating here. We'll use it again later. Okay, but you might be saying, oh, but wait a minute, you didn't tell me the full configuration. How can I solve this problem? And that's the beauty of the finite state machine. Okay, the beauty of the finite state machine is if I tell you my current state and what's coming, I don't need to know how you got to the current state. So let's see this in action. I'm in Q0. I don't care what's happening here. I'm about to read the 0. So I'm in Q0, I'm about to read the 0. Okay. In fact, we could have deduced that, if you're in Q0, you haven't processed anything yet. But you're in Q0, you're about to read the 0, so you read the 0, you come to Q1. And then you'll read another 0, you'll stay in Q1, another 0, you'll stay in Q1, and you'll say yes. Okay. Here you're in state Q1, you don't care how you got there, and you're about to read a 0, so you stay in Q1. Then you read a 1, then you move to Q2, then you read a 0, then you stay in Q2, and you say no. Okay. So, important. In a finite state machine, if you know your state and the future bits to come, you don't care, you can say yes or no without knowing, okay, the previous bits. In other words, you don't need to know how you got to the state Q0 or Q1. You don't need to know how. You can immediately say yes or no. Okay, so that's important. All right. So now, when we're talking about these type of computing machines, there are sort of two questions that we would like to ask. Okay, so the first question is, so here's a computing machine, right? What problem does it solve? So effectively what I'm asking is, for what strings does it say yes? Okay, so let me erase this. For what strings for what input strings does M say yes? Okay, you can think of that as the yes set of M. We call that the language or the problem that's solved by M. So we say that the language of M, the problem that's solved by M, the language corresponding to M is exactly this yes set, is the strings for which M says yes. Okay, so now if I asked you what's the yes set for this, we're really typically just asking you for a description of this yes set. Now we have various ways to describe it. We can use variables, we can use regular expressions, we can use recursive definitions, but in general, the first step is to come up with an English description. So let's look what happens in this machine. Okay, you start at Q0. If nothing comes, so if your input string is epsilon, you stay here forever, you're done. Okay, and you reject, you say no. Sometimes we say yes means accept, no means reject. Okay, so you say no, reject. Okay, and if a 0 pops, then you say you sort of go into the accept state, and you're waiting. And if as long as more zeros come, you will remain in this accept state, this yes state, and you will say yes. The moment you see a 1 from either Q0 or Q1, you move into this kind of this kind of black hole state, this kind of sink state from which you can never escape, because whether you get a 0 or 1, you will always stay here. And what brought you here is a 1. So if the string starts with a 1, you're done. You will never escape from this reject state or no state. If you get into the accept state but then ever see a 1, you will reject. So basically this machine is rejecting or saying no to any string that has a 1. Okay? And also it's rejecting the empty string. So it accepts all strings with a non-zero number of zeros and only zeros. So the language of M in this case is strings with only zeros and at least one. At least one. Okay, so it's the language is 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, and so on. Strings with only zeros. So we could, if we wanted to use sort of set and variable notation, they're the strings W, where W is equal to 0, concatenated, raised to the concatenated power n, where n is greater equal to 1. Okay, so we figured out the language that is sort of, we say that this problem is solved by M. We say that's the language that's accepted by M. The language of yes strings for my machine M. Okay, now, you can get lots of practice with this type of question. So, question. I give you a machine M and I ask, what is L of M? What is the language that it solves? Okay, so I give you a machine M and I ask you what's the language that it solves, and exercise 24.2, lots of practice with this, and get that practice, okay? Because these are very important machines, okay? Finite automata. So I give you a machine, just like here, and I say, what's the language it solves? So we go through exactly this kind of an exercise. The other kind of question we like to solve, and this is the one we are more interested in, is I give you a problem, I give you a language. Question. I give you a problem, i.e., now we know what a problem is, what a computing problem is, i.e. a language, L, and I ask you to construct a machine that solves that problem. Okay, so what I'm asking is, can you construct a finite state machine, like this? Okay, and we typically will represent them with these transition diagrams. So can you construct a finite state machine for which the yes set is exactly that language? And anything that's not in that language, the machine will say no. Okay, so that's what we're going to discuss next, and we're going to do, we're going to discuss it through examples. Okay, so I give you a problem, i.e. a language L, okay, and I ask, can you find a machine M for which, the problem solved by M, so L of M is equal to L. Okay, so that's the question. Okay. In other words, designing a finite state automaton, designing DFA, sometimes we call this a Deterministic Finite Automaton, or DFA, or Finite State Machine, Finite Automaton, designing an automaton to solve a particular problem. Let's talk about that. So let's erase. And we'll go through sort of some of the interesting, thought processes that are involved in designing an automaton to solve a problem. Now that's kind of like writing a program. Okay? I give you a problem, you write a program to solve it. Okay? And so, very often some kind of creativity is involved, so there are no real rules for this. You just have to think about the problem and design the automaton. So let's do some examples. Okay? So here's a language. It's just 0, 1. This is the string 0, 1. Incidentally, what if I wanted to also accept the empty string here? Okay, so think about that problem. What if I wanted to accept the empty string here? What would I do? Okay. So I wanted n greater equal to 0. How would I change my automaton? Okay, so let's consider this language. It's a very simple language. It's an example of a finite language. Okay, and I have to design an automaton that accepts this finite language. It's just containing the string 0, 1. So everything else you must say no. Turns out that even though the language is very simple, this is not a trivial problem. We have to think about it and solve it in a systematic way. And you can pretty much use this systematic way for any finite language. So in some sense, I'm demonstrating to you that any finite language can be solved by a DFA, by a finite automaton. Okay. So as usual, we're going to start in our start state Q0. Okay. Now, if I get no string, I'm not going to accept. So this cannot be an accept state. If I wanted to accept the empty string, my start state would have to be an accept state. Okay. Now here's my thought process for how I'm going to build the machine that accepts this language. And now I highly encourage you, go for it. I'll give you a few seconds. Go try to build a machine that solves that language. Okay, I'll give you 5 seconds. 1, 2, 3, 4, 5. Okay. Now, if you're coming back, if you paused and solved it, great. If you're coming back just for the ride, here's my thought process for solving this problem. Okay. So, first thing I look at is the string 0, 1. It doesn't start with a 1. So if I'm going to see a bit 1, if I see a 1, I'm done. I can immediately reject. So let me move into a state. Now, of course, I said we typically label the states Q0, Q1, Q2, and so on, but you can choose whatever labels you want, and it helps a lot to choose labels that remind you of what's going on. So I'm going to call this the error state E. Okay. If I start with a 1, I go into the error state, and I'm never going to leave this error state. Okay. So when we're done with all the bits, I'm going to reject. I'm going to say no. Okay. So think of that as an error state. Now, the reason I don't immediately, jump up and down and say no is because those are not the rules by which these finite automata operate. Okay. Even though technically by human intuition, human logic, we know that once you get here, because it's a sink, you're going to reject, you could stop the computation. That's not the way finite automata works. So that's not the way programs work. When you're running the program, it runs until execution end. Okay. So it's going to continue processing all the bits. Even if you get 0, 1, 0, 1, 0, 0, 0, 0, and so on, it'll still process and stay here. Okay, on the other hand, if I get a 0, okay, I'm going to transition to a state Q1. Now, supposing I don't get any more bits, I cannot accept. So this is not an accepting state. Okay? So I cannot call this an accepting state because then I would accept just the bit 0. Okay? So you can think of this as the state. I've partially seen the string and I'm waiting. What am I waiting for? I'm waiting for 1. Okay? So if I find a 1, if the 1 comes next, okay, then I should be ready to accept. So let me call this state Q2, and this is an accept state, and now I'm not going to use green, I'm going to use the 2 circles. Imagine that I've colored it beautifully with green. Okay, so if I get a 0 or a 1, I'm ready to accept. Okay, now this is not a well-defined automaton yet, because you have to tell me what to do if in this state I didn't get a 1. If I got a 0, it means I've seen the string 0, 0, but that's not here. It's not in my set, so I had better go into this, error state. So if I see 0, 0, I'm done. Okay. What about here? You have to tell me what to do if more bits come. So you've got 0, 1, but if 0, 1, 0 comes, then I know it's not the string and I should reject. If I get 0, 1, 1, I know it's not the string and I should reject. So if any other string comes, if any other bit comes, I should reject. So there. And that's the complete automaton. Okay. So now you can compare this with your solution and see if you got this solution. If you did, fantastic. Okay. Meanwhile, if you didn't, sit down and see if you understood, go through the logic of how we created this and give yourself another problem. Maybe try, can I construct an automaton that recognizes the language 0, 1, and 1, 1? Okay, so exercise. What about the language 0, 1, 1, 1? Okay. Well, you see, it's similar, except that in this one, you cannot immediately go to the error state because you never know. Maybe another one will come. So you're not quite ready to declare no. Okay. But see if you can design this automaton. Basically, any finite language can be done with an automaton if you sit down and put the effort and do it. Okay. Let's take another couple of examples. Okay. The vending machine. So this takes us closer to reality. So you've seen a vending machine. I claim it's just a finite automaton. So let me describe for you, the vending machine. So in the vending machine, what do we have? We have, you can accept coins. And let's assume that the vending machine takes 5-cent and 10-cent coins. Okay, so this is just a real-world example of an automaton. So, and let's imagine that a Coke costs 25 cents. So every time the machine gets 25 cents, it should spit out a Coke. Okay. So, initially, the machine starts in some state. Okay. And we typically call that Q0. But now I'm going to use labels to tell me what's going on. I'm going to call that the 0-cent state. Okay, so this is where we start. Okay, now I'm going to imagine you're putting coins in. Think of the coins as the input sequence. So we've deviated a little bit from binary strings because we're interested in, real world applications now. Or since this machine only takes 5 and 10 cent coins, you can think of the 5 as 0 and the 10 as 1. And the string of 5 and 10 cent coins that have been put in can be represented by a string of zeros and ones if you want. But let's just keep with the real world and talk about 5 and 10 cent inputs. The sequence of 5 and 10 cent coins that come in, tells the machine what to do. Okay. If it gets a 5-cent coin, well, it should transition. So 5-cent coin, it should transition. Well, what's the natural state into which it should transition? Well, I was in 0 cents. Now I've got 5 cents. So I have 5 cents in me. So think of the state of this machine that I'm building as storing how much money I have. How natural is that? Okay. And so tell me, if I'm in my 0-cent state and someone put in a 10-cent coin, what state should I go to? That's not hard. If you give me a 10-cent coin, I'm going to go to the 10-cent state. Okay? There are no other coins. So from 0 cents, I can either go to the 5-cent or the 10-cent state. Now it gets interesting. From the 5-cent state, maybe someone's already put in 5 cents, so I'm in the 5-cent state. Now you can put in a 5-cent or a 10-cent coin. If you put in a 5-cent coin, I go to the 10-cent state. If you put in a 10-cent coin, this is where it gets interesting. I go to the 15-cent state. Okay. What about here? If you have 10 cents and you get a 5-cent coin, you go to the 15-cent state. If you have 10 cents and you get a 10-cent coin, you go to the 20-cent state. If you have 15 cents and you get a 5-cent coin, you go to the 20-cent state. If you have 15 cents and you get a 10-cent coin, now this gets very interesting. Okay. Well, in theory, you have 25 cents, but you have to send out a Coke. When you send out the Coke, you got to charge that 25 cents. So actually, you go to the 0-cent state with a 10-cent coin. Okay. But I will label this with an action also. So not only do you transition, but you dispense a Coke. Okay. Because you have 25 cents. And so you dispense the Coke, your 25 cents goes to 0, so you go to the 0-cent state. What about from 20 cents? Well, if you get a 5-cent input, similar process. You have 25 cents, dispense the Coke, and come down to 0 cents. Okay, so this is 10 cents. Oh, this is 5 cents. This is 10 cents. This is 5 cents. Okay, but this is 10 cents. So I'm just labeling all the. If you get a 5-cent input from 20 cents, you go to 0 and output a Coke. what happens if you get 10 cents in the 20 cent state? That's interesting also. Okay. Now you have 30 cents. Well, technically, you don't have 25 cents, but you have more than 25 cents. So you should certainly output a Coke. Okay. But where do you go to? Well, after you output the Coke, you have 30 cents minus 25. Okay. So you should go to the 5 cent state. 30 minus 25 is 5. So if you get an input of 10 cents, okay, you output a Coke and transition to the 5 cent state. And there it is. That's the operating of the vending machine. The vending machine is a finite state machine, except that you've augmented some of the transitions, okay, the edges that take you from one state to another. You augmented some of the transitions with some other action as well. So you not only transition states, but you reach, take a Coke, and dump it. Okay? Finite state machine. So the vending machine is a very simple finite state machine. But, finite state machines can do all kinds of complicated things. Okay? So let's take another example. Couple more examples of designing finite state machines. So that's the vending machine. Okay, so let me specify two languages. L1 equals strings with a 0. So they could have more than one 0, but they have at least one 0. And L2 is strings ending in 1. Okay, so let me show you that I can represent both of these with regular expressions. So this is strings with a 0 is sigma star. Remember what sigma is. Sigma is the alphabet 0, 1, and then the star takes all concatenation. So this is all possible binary strings followed by a 0, followed by sigma star. Okay, so that's as a regular expression. And now sometimes we don't want to keep writing sigma star. Okay, and so we have this wildcard symbol, which we just call star, 0 star. And this was exactly the kind of format that I showed you in the first example of a regular expression, ls, list, fox, star. Fox concatenated with sigma star. And this is the language, any string, but it must end in a 1. So it's sigma star, anything, followed by a 1. Okay. And anything could even be the empty string, okay, which, is the wildcard. We just typically call this the wildcard, followed by 1. Sometimes we even forget. Sometimes once we're experts, we don't even put the concatenate sign. We might just write this as star, 0, star. And the concatenation is implicit. We might write this as star, 1. Okay. Anything 0, anything. Anything 1. Okay, so let's build automata for these two problems. Okay, so now I'm going to pause the video. Or you pause the video. 1, 2, 3, 4, 5. Solve the problem. 1, 2, 3, 4, 5. Okay, here we go. Let me show you my logic, my intuition for how to build this automata. So, well, we usually start in my state Q0. Okay, and the empty string is not accepted because, it must have at least a 0, so I cannot accept the empty string. Now, okay, if I get a 0, actually I'm ready to accept, because all I need is 1 0 in my string. So I'm ready to accept. So I'm ready to accept in my state Q1, so I'm going to call it an accept state. And in fact, it doesn't matter if any other strings come. If any other bits come, I'm ready to accept. So this becomes a black hole state. But unlike the previous example where the black hole state was an error state, a no state, in this case, the black hole state is a yes state. So you cannot leave this state no matter what comes, no matter what 0s and 1s comes, because you've already found the 0 that you need to accept. Okay. On the other hand, now you're in state Q0, if 1s come, you just don't leave this state. You stay in this state. You think of this state, the 0 state, as I'm waiting for a 0. So 1, 1, 1, 1, 1, I stay in this state. 0 comes, boom, ready to accept. It's a black hole state. Okay. Now, I've shown a particularly efficient way of, building a machine to solve that problem. You might have solved it with 3 states or 4 states. That's not a big deal. Don't worry. As long as your solution is correct. Now, yes, just like programmers like to find the smallest program that can solve a problem, people are interested in the smallest finite state machine that can solve a problem and so on and so forth. But for the moment, we're happy with just some finite state machine that solves the problem. Okay. So if you did it with 3 states, don't worry about it. It's a good solution. Okay, let's talk about strings that end in a 1. That's a bit harder. This one's easy because, the moment you see a 0, you're ready to accept. Strings that end in a 1. Okay, so let's perform the usual logic. We start in my start state Q0. Okay. As long as I see zeros, I'm not going to leave the start state. It's kind of like here where I see ones. So if I see zeros, I stay here. Okay? I'm not going to budge. The moment you give me a 1, I feel like I'm ready to accept. You've given me a 1. I'm ready to accept. Okay? So I'm ready to accept. Let's call this Q1. I'm ready to accept. And if I make this a black hole state that's ready to accept, the problem that will arise is that if another 0 comes and that's it, my string doesn't end in 1. So I cannot make this a black hole state. I can make this I can stay in this state as long as I continue to get 1s. Okay, as long as I continue to get 1s. Okay. But if I get a 0, I have to go back to this waiting for a 1 state. So you can think of this as waiting for a 1. I get my 1, ready to accept as long as I keep getting 1s. If I get a 0, I go back to the waiting for a 1 state because I have to end in a 1. So the only case where I can stay in this state is if the last bit is 1. Okay. Now if you solve this problem, again, you might have used 3 states, 4 states. That's not a big deal. Okay. But try to sort of get good at looking at a problem and trying to visualize the process of constructing a finite state automaton to solve the problem. Okay, so here are 2 example languages. Now, let's see if I can do even more complicated languages. Okay. So let me erase here. Let's talk about more complex sets, and one way to get more complex sets is to take sets that you already have and perform set operations on them. So let's look at the set operation. So we have complement, so set operations. Okay, so we have complement, union, intersection. Okay, and languages are sets, so we can do any set operations that we can do on sets, we can do on languages, and we saw two other operations we do on languages, which is this thing called concatenation and clean start. Okay, so we have concatenation and clean start. Okay, so these are set operations. So let's see. Okay, so here's a language, okay, and here's a machine that solves that problem, that solves that language. So what about the complement? So L1 complement. Okay, now we can describe those strings, that do not have a 0. Strings with no 0. And L2 complement. L2 complement equals strings with ending that do not end in 1. Okay. So doing the complement is especially easy. So I'm going to pause the video for a few seconds, pause the video, and figure out what machines solve the complement. So 1, 2, 3, 4, 5. Let's do it. Okay. I'm going to take the same automaton, the same machine, Q0, Q1, okay, which goes 1, 0, 0, 1. Okay. Now, let's see. To solve this problem, if I said yes here, I should say no here, because a string is in this set if it was not in that set. And if I said no here, I should say yes here. So all I have to do is switch the yes and no states. So boom, switch the yes and no states. So this becomes my new yes state. Done. We've implemented the complement. So if you give me any language and you show me a machine that solves that language, I can solve the complement with almost no effort. I just flip the yes and no states. Okay. So complement, if a language can be solved, if a problem can be solved by a finite automaton, the complement can be solved. Okay. Let's talk about, so here are 2 languages, L1 and L2, and here are finite state machines that solve L1 and L2. Can I solve the intersection? Can I solve the union? Okay, so can we all solve the union, L1 union L2. What about L1 intersection L2? Okay. So now we're getting into some more sophisticated methods for designing automata. Okay. And I'm going to show you a nice trick that's called product states. So you don't need to reason about what the union is or what the intersection is. I'm going to show you that we can solve the union directly using the two machines that solve the individual languages. Okay. So we can solve, so let's name these machines, M1 and M2. So we can solve the union, L1 union L2, and the intersection, L1 intersection L2, without reasoning about the languages, by just using the machines, by just using the machines M1 and M2, okay, and then constructing a new machine to solve the problems that we're interested in, and constructing a new machine, let's call it M. Okay, directly constructing a new machine M without even looking at the languages. All I need to know is that M1 solves L1 and M2 solves L2. Now I'm going to show you how to construct M to solve the union. The same method works to solve the intersection. Okay. The idea is simulation. I'm going to simulate the running of M1 and M2 in a single machine M. So the idea, simulate the running of M1 and M2, using M. Okay. So let me tell you what I mean by simulate the running of M1 and M2. So if I'm going to simulate the running of M1 and M2, I must certainly be able to simulate the start configuration. So if I'm starting on a string, let's imagine that I start on a string. Okay, where does M1 start? M1 starts, okay, so now I'm going to be a little more careful. I can label the states any way I want. So let me label these states, S0 and S1. S0 and S1. It's the same automaton. I've just relabeled the states. But I don't want to have multiple states that are labeled Q0 and Q1. Okay, so to remove confusion. Okay, so if I'm thinking of running both M1 and M2 on a string, where do I start? Well, I start with M1 in state Q0 and M2 in state S0. So I'm going to simulate this process. So I'm going to imagine a start state, which is, Q0, S0. You can think of this as saying, that says that M1 is in Q0 and M2 is in S0. Okay. And this is where this machine that simulates M1 and M2 starts, because M1 is in Q0, M2 is in S0. Now let's see what happens, okay, when I get a 0. Okay, so if I get a 0, okay, what happens to M1? M1 transitions to Q1. What happens to M2? M2 stays in S0. Okay, so if I get a 0, okay, M1 transitions to Q1 and M2 stays in S0. So I'm gonna say that my machine that's simulating them both, okay, transitions to the state Q1 for M1 and S0 for M2. So that's the way we read this state. It's kind of encoding that M1 is in Q1 and M2 is in S0. Okay. What happens in this? What happens, from the beginning if I get a 1? If I get a 1, well, M1 stays in Q0 and M2 goes to S1. So if I get a 1, okay, M1 stays in Q0 and M2 goes to S1. So I'll transition to a state that represents that. Okay, Q0, S1. M1 is in Q0, M2 is in S1. Okay. All right. Okay, good. So that's what happens at the beginning. Okay. But now let's think. So I've told you what happens from the starting state. Okay. Now what happens from this state? Let's think about what this state is. This state says that, M1 is in Q1 and M2 is in S0. So you're in Q1 and S0. What happens if you see a 0? M1 stays in Q1, okay, and M2 stays in S0. So if you see a 0, M1 stays in Q1 and M2 stays in S0. So if you see a 0 in this state, which represents, M1 is in Q1 and M2 is in S0. If you see a 0, M1 stays in Q1 and M2 stays in S0. What about in this state if you see a 0? So you're in Q0 and S1. If you see a 0, you transition to Q1, S0. Okay, so if you see a 0, you transition to Q1, and this guy transitions to S0. Q1, S0. This is what happens in this state if you see a 0. Okay, so we have Q0, S1. When you see a 0, transitions to Q1, S0. So this is a 0 here. Okay? All right. Now, in this state, Q1, S0, so Q1, S0, what happens if you see a 1? You stay in Q1 and you transition to S1. So Q1, S0, if you see a 1, you stay in Q1, you stay in Q1 and M2 transitions to S1 if you see a 1. Okay. What happens in this state if you see a 1? So you're in Q0 and S1 and you see a 1. You stay in Q0, S1. You stay in Q0, S1. Okay, so this state, if you see a 1, you stay, M1 stays in Q0 and M2 moves into S1. Okay. So this is what it means for M to simulate the running of both M1 and M2. Its states capture the states of both M1 and M2, and it makes the transition that reflects the actual transition that those two machines make. Okay. Is this automaton done? Not yet, because I need to tell you in this state of my new machine M, okay, what happens when you see a 0 and what happens when you see a 1. So you're in Q1, S1. You're in Q1, S1. Okay, when you see a 1, you stay there. 1 keeps you in Q1, 1 keeps you in S1. When you see a 1, you stay there. What happens when you see a 0? Well, Q1 stays there, but S1 transitions to S0. So you transition to Q1, S0. So if you see a 0, you transition to Q1, S0. Okay. So there's an interesting automaton. Okay, I claim that this automaton M simulates the running of M1 and M2 simultaneously. Now let's see that in action. Okay, so let's see that in action. So let's consider the string, let's say 0, 0, 1, 0. Okay. So what happens with M1? So let's talk about M1. So we start in state Q0, okay, and we're processing 0, 0, 1, 0, 0, 0, 1, 0. Okay. With respect to M1, so the machine M1 under the machine M1, the state Q0 when you see 0 is going to transition to Q1. So you've processed the first bit, and now you're processing 0, 1, 0. Okay, so you've gone to Q1. You're in Q0, you see 0. You go to Q1. Okay, you're in Q1, you see 0. You stay in Q1. You're in Q1. Okay, so you stay in Q1 and you've now processed both zeros. Okay, you're in Q1, now you process the 1. Okay, so you stay in Q1. And you're ready to process the 0. So this is all M1. This is M1. Okay, and one final processing step. You process a 0, you process the 0, you stay in Q1. And now you're done. Okay, and M1 would say yes. Okay, let's look at what happens in M2. So you're processing this string. So you start in state S0, and you're processing the string 0, 0, 1, 0. Okay, you process the 0, so the 0 keeps you in S0. So under M2, you stay in S0, you've processed the 0, and you have remaining 0, 1, 0. So you process another 0, you stay in S0. You stay in S0. Okay, so you process 2 zeros. Now you have 1 0 left to process. So you process the 1. So it transitions you to S1. and you process 0, 0, 1, and you have a 0 to process, and one final bit, you're in S1, you process the 1, okay, you're in S1, you process the, you're in S1, you process the 0, takes you back to S0. S0, and you've now processed all the bits, and you're done. Okay, so here, M1 says yes. Okay, M2 says no. Okay. Now, quick exercise for you. Okay, do it before I do it. Well, I'll pause the video. Okay, do the trace of the computation for M. So let's call this guy M. This is M. Okay. So let's do it. The start state is Q0, S0. So we have Q0, S0. Okay. And we have all the bits to be processed. 0, 0, 1, 0. We process the first 0. That takes us to Q1, S0. And we process the first 0. And we have 0, 1, 0 left. So Q0, S0, the first 0 takes us to Q1, S0. We process the next 0. And the next 0 keeps us in that state. So we're in Q1, S0. We process the second 0. Okay, and we have 1, 0 left to process. Okay, so we process the 1 from this state Q1, S0. So we process the 1, and the 1 takes us to Q1, S1. And we process 0, 0, 1, and we still have the 0 left to process. Okay, by the way, this is M under the influence of M, under the influence of M, under the influence of M. So I'll draw a line here, and a line here. Okay. And now we process the final bit. So under the influence of M, we are in state Q1, S1, and we process the 0. So that takes us back to Q1, S0. And we have no more bits to process. Okay. So you see how convenient this sort of way of representing the configuration of the computation and this whole computation trace is. Okay, now what I want to show you. Let's track the progress of M1. So it starts in Q0, then it goes Q1, 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 Q1. But look at what M did. Starts in Q0 and then went Q1, 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 Q1. Let's track the process of M2. It starts in state S0, then it goes S0, 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 S1, S0. And look, S0, 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 S1, S0. M is simultaneously running both M1 and M2. And at any stage in this guy's computation, we can look at what my state is and we will be able to figure out where's M1 and where's M2. Okay, now, let's say we want to do the union. So if we want to do the union, okay, so you should say yes if, either of these guys says yes. That's what the union means, strings that are in the union of these. Okay, so you combine all the strings. So if we wanted to do the union, M1 says yes, M2 says no, you should say yes. Okay, so for union, M should say yes. For intersection, M should say no. Intersection means that both of them must say yes. So you must be in both sets. Okay. Now, how would we implement that? Okay. So the only thing that is missing from my automaton is what are the accept states, what are the yes states, and what are the no states. Okay. It's the only thing that's missing. So what are we going to do? If we want to do the union, okay, the accept states should be either, so you can look at the individual states, okay, and if either of those individual states is an accept state for the corresponding automaton, okay, it should be an accept state of the union automaton. So for union, yes state are states which are yes for M1 or M2. Intersection, yes states are yes states are states which yes for M2, for M1 and M2. So if I'm doing the union, I set the yes states as the or. If I'm doing the intersection, I set the yes states as the and. So let's look at that in practice. So if I want to do the union, Q0, S0, both are no states. So this is a no state. Okay. Q1, S0. Okay. Q1, S0. Well, it's a yes state for M1. So this becomes a yes state if I'm doing the union. Q0, S1. So Q0, S1. Well, S1 is a yes state. So this becomes a yes state if I'm doing the union. Okay. And then Q1, S1. Well, Q1, S1 is a yes state for both. So this becomes a yes state if I'm doing the union. And there I have finally specified my automaton M that does the union of these two languages. Okay, now you should feel comfortable that, no matter what automata you give me, I can do the union using this process. These states in here are called product states. For the obvious pictorial reason that it looks like I'm taking a product of the states. How many states are there in my union automaton? The product of the number of states in here times the number of states in here. So here I have 2, here I have 2, 2 times 2, 4. That's why I have 4 states in here. Another reason why we call them product states. Okay. Now let's say I was doing the intersection. Okay, so let's say I'm doing the intersection. So this is the union automaton that implements the union of the languages. If I'm doing the intersection, okay, then my yes states must be yes states for both automata. Okay, and the only state that's a yes state for both automata is Q1, S1. So that's Q1, S1. There is the automaton that does the intersection. That's it. Okay, so the idea is I'm going to create an automaton that simulates both together. Okay, and then at the end, decide which are yes states and which are no states, depending on whether I want to do the union or the intersection. Wow! So complement, no problem. Union, intersection, no problem. Okay, now complement was easy. I just flipped yes and no. But union and intersection are a little bit harder because I have to sort of build this simulating automaton and then, decide which are the yes and no states based on which are the yes and no states of my original automaton. So let's summarize. Okay, so what have we seen? Okay, so summary. If L1 and L2 can be solved by, now I'll call them a DFA, so Deterministic Finite Automaton, then, okay, L1 complement, L2 complement can be solved. Okay, so what does it mean that can be solved by a DFA? It means that we can build a machine that solves that problem, that says yes whenever a string is in the language and no whenever a string is not in the language. Okay. So if L1 and L2 can be solved, then the complements can be solved. Trivial. Okay. The union can be solved. Can be solved. Okay. The intersection can be solved. And and here you just flip the yes states and no states. Flip yes and no states. Here you have to use product states. Okay, and it also turns out that L1 concatenated with L2 can be solved. L1 star can be solved. So you can do concatenation, you can do the clean star. L2 star can be solved. Okay, now I won't cover this. You can see the details in the text. Here you need another trick. Okay, and the trick here is what are called subset states. This is much harder. So product states, you multiply the number of states times the number of states. Subset states, more complicated. For example, to do the clean star, you might need subset states. Okay, so all possible subsets of the states. Well, it's a little more complicated, but it can be done. Okay. So this means that if you have any languages that can be solved by DFA, and what else do we know? Okay, any finite language can be solved. Okay, that's what started the whole discussion. We did the language that only contains 0, 1. So finite languages can be solved. If you have any languages that can be solved, you can combine them with the complement operation, the union, the intersection, the concatenation, or the clean star. So you can get more complicated languages with all these operations. Okay, and they can be solved. Okay, now we haven't proved it, but we've given all the details, all the necessary sort of details for you to go and complete the proof, or even you can read the book. Okay. But what are these? These are exactly the kinds of operations that we use in regular expressions. So let's remind you of regular expressions. So regular expressions. Okay, regular expressions. The building blocks, the starting points are finite languages, finite. And then, you can take your finite languages and combine them with, complement, intersection, union, concatenation, and clean star. Okay, so those are the regular expressions. You take finite languages, but those can be solved. You can combine them in with complements, intersections, unions, concatenation, clean star, and whenever you do this combination, we know it can be solved. So it means that finite state machines can solve all regular expressions. In fact, it also turns out that any finite state machine problem, any problem a finite state machine can solve can be described by a regular expression. But what we have shown is that finite state machines can solve all regular expressions. Wow! So any language that you can express as a regular expression, that you can describe with a regular expression, can be solved by a finite state machine. Theorem shows you the power of the finite state machine. Any language that can be described by a regular expression can be solved by a DFA. Now, we didn't give all the nuts and bolts of the proof. We showed that, at least by example, we showed you how you do complement, how you do union and intersection. We didn't get into the details of concatenation and clean star. Okay? But, at least we have sort of motivated this theorem. You can see some of the details, some more details in the text. And then if you want the full proof, you can go to more advanced texts. Okay. Now, for this reason that, any language that can be described by a regular expression can be solved by a DFA, the languages solved by DFA are sometimes called regular languages. So languages, i.e. problems solved by DFA are called regular languages. So if someone says, you have a regular language, it means that you can solve it with a DFA. Okay. So powerful machines, these simple state transitioning machines, can solve any regular expression, can solve any language described by a regular expression. Wow. Hit myself on the head for that. Okay, let's erase and see what the limits of this power are. Are there any limits to this power of the DFA? So we know that they can solve all regular expressions. What more can they solve? Turns out they cannot solve any more than regular expressions. And so now the goal is to describe a single problem that they cannot solve. Okay? And it's going to turn out that this is such a simple problem that we're going to look at the DFA and say, wow, you cannot solve this simple problem? Well then, I need more. Okay, so here we go. Okay, so what we have learned so far, that DFA, finite state machines, are very powerful. They can solve all regular languages. So here's a pop quiz. Pop quiz. Okay. For the language L, which is zeros followed by ones, Okay, so 0 to the n followed by 1 to the m, where n and m are greater or equal to 0. Find a finite, give a finite state machine. Get a DFA that solves this problem. So sit down and work it out. Good practice. Okay, now, I'm going to consider a similar language, L, which is equal to, zeros, followed by an equal number of ones, 1 to the n, 0 to the n, 1 to the n, where n greater or equal to 0. Okay, so it's similar. Okay, what's the difference is this equality. Okay, so it's an equal number of zeros and ones. So if you're going to test membership in this set, so you can only say yes when there are an equal number of zeros and ones. So you can think of the DFA that solves this problem as a DFA that can test for equality. So this is sort of like testing equality. Is the number of ones equal to the number of zeros? So we'll call this LEQ. Now, I'm going to show you a stunning result, and if I show you a stunning result, you should not believe me. So you should ask me for proof. I'm going to give you proof even if you don't ask me for proof. Okay. So what's this stunning result? Okay, it's going to be the result is deep, and the proof is going to be a beautiful application of Pigeonhole. So what is the result? Theorem. LEQ. So this problem, remember, language is a problem, cannot be solved by DFA. And I'm going to underline cannot. We are not saying Malik cannot solve it. Okay, maybe someone smarter than Malik with superior DFA programming skills might be able to solve it. Maybe a Martian might be able to solve it. No! There is no DFA that can solve this problem, i.e. there's no DFA that can test for equality. Okay? And you say, what? And I say, yes. And then you say, okay, you better prove it to me. So I will. Proof. Okay. And the proof is a proof by contradiction. Contradiction, very powerful. By contradiction. Okay, so you might wonder, how would such a proof go? Well, we say, well, suppose it can be solved. So suppose it can be solved by a DFA. So if it can be solved, then there's some DFA that solves it. Well, then that DFA has some number of states. So you better be able to tell me how many states it has. Well, maybe you don't know, but it has to have some number of states, because that's what a DFA is. It has some number of states. So let's say a DFA with k states. We don't know what k is. Okay. But we know that, it's some finite number of states. Deterministic finite automaton. Okay. So what I'm going to do is I'm going to consider what happens to when we feed in a particular string to this DFA. What's that string? A whole bunch of zeros. In fact, consider the string 0 to the k, which is just 0, 0, 0, 0, ... 0, k times. K times. Okay, so let's think about what this DFA does. So it starts in some state Q0, and it's got a bunch of states. Okay, and then when it processes the first 0, it moves to a state. Then it processes the next 0, it moves to a state, and processes the next 0, and so on. So it transitions from one state to another as it's processing this string. Okay? So let's see. So you start in state Q0. Okay, when you get your first 0, you move to state. When you process the first 0, you move to state of 0. I'll just call it state of 0. I don't know what it is. Okay, and then when you get your next 0, when you process the next 0, you move to state of 0 squared. Okay, and then state of 0 cubed. And so on up to the final state of 0 to the k. Okay, so it's just moving from one state to another, and since it has to process k0, it jumps around, k times, starting from state 0, state q0, and at the end it comes to rest. Okay. Now comes the big blow. Okay, what's the big blow? Well, the big blow is that in this processing, we are visiting state 1 state, 2 states, 3 states, 4 states, okay, and all the way up to the state of 0 to the k. So this, so 1 0, 2 zeros up to k0. So you visited k states here plus 1. So you visited k plus 1 states. But wait a minute, there are only k states. So by the Pigeonhole Principle, that means that 2 of these states must be the same. 2 states must be the same. Okay, and that is Pigeonhole. Okay, so for example, this state, state of 0 to the 2 and some other state, maybe here. Okay, so let's call this state I,
and this state j, where I is less than j. So state after you've processed 0 to the I is equal to state after you've processed 0 to the j, okay, which we will just call some state q, just so that we don't have to say that long thing. How do we know that? That's Pigeonhole. Because you visited k plus 1 states. It had better be the case by Pigeonhole that Pigeonhole tells us that 2 of the states must be the same. Okay, so let me show you what's going on. So we've processed 0 to the I. So we've moved along and processed 0 to the I. So here's my state for 0 to the I. Okay, I processed 0 to the I. Now, when I process the remaining bits that take me to 0 to the j, so j minus I bits. So when I process the remaining bits, okay, so 0 to the, after another 0 to the j minus I bits, it takes me back to the state 0 to the I. Okay, wonderful. Now let's consider what happens. Okay, so now we have a DFA that solves LEQ. So let's call this DFA M. So M solves LEQ. So M, when you feed it 0 to the I, 1 to the I, okay, what should it say? Yes or no? I'll give you 2 seconds. It's easy. It should say yes. It should be yes. Why? Because I equals I, and so it's in this language, so M should say yes. And M, when it's fed 0 to the j, 1 to the I, should say no. Because look, j is not equal to I. So j is not equal to I, so it should say no. Okay. But now let's see. We have derived a contradiction. Why? Because after M has processed 0 to the I, it's at state, this one here, which we've labeled state of 0 to the I. Okay. Now, okay, it processes 1 to the I. So from here, it processes 1 to the I, and ends up in state whatever. And that must be a green state, a green accept state. Okay. Why? Because it says yes. Okay. Now let's look at what happens when it processes 0 to the j. So it's processing 0 to the j. In the process, it processes 0 to the I and then the remaining j bits and gets back to this same state. Okay. And from this same state, now it has to process another 1 to the I. So it processes 1 to the I and it's a finite state machine. So it doesn't need to know how did I get to this state. I'm going to process this 1 to the I, from the state that I processed before. Okay. And so it must lead me along the same path to this green state. But that's a contradiction, because this guy's got to say no. But it's led me to the green state, which says yes. Okay? And that's the idea. That's the contradiction. Let's make it a formal argument. So, while it's processing 0 to the I, 1 to the I, it's after it's processed 0 to the I, okay, its configuration is after, so in this string, after 0 to the I, the configuration is it's in state Q, because it's processed 0 to the I, so it's in state Q. Okay, it's processed 0 to the I, and now it's getting ready to process 1 to the I. Okay. In this string, after it's processed 0 to the j, after 0 to the j, the config is in the state Q, because it's processed 0 to the j, and it's processed 0 to the j, and it's now ready to process 1 to the I. Okay. And we saw in our very first exercise that, we don't care what we processed. Okay. All that matters is what is the current state? Same. And what remains to be processed? Same. Okay. So that means that M must produce the same result for these two scenarios. So it implies, same result. And that's the same contradiction we had before, because we know it has to be a different result. Contradiction. Fishy! And that's the end of the proof. Bam! Pigeonhole in action. Boom! Okay, that's the end of the proof. So that means that this DFA cannot exist. Just cannot exist. So here's a problem that cannot be solved by DFA. Now what's the intuition? Okay. The intuition is that however many states you have in your DFA functions like a primitive memory. You can sort of remember what's gone on by what state you're in. But that's the only memory that the DFA has. There's no external scratch pad where you can jot things down. Now you think about when you are doing math or whatever, doing anything complicated, you have a scratch pad on which you can jot things down. Essentially, you have an external memory. Okay? The DFA has no external memory, has no way to count. Okay? Now, if it's going to remember how many zeros came, okay, it needs a way to remember n. Okay? And the only way it can remember n is using its states, but because it doesn't have an external scratch pad. And once n gets large enough, it cannot remember how many states arrive because it has to now start repeating states. Okay? So it might be in some state when I have come, and then it's going to have to repeat that state when j have come, and that's a problem. So it's an ambiguity. It cannot remember how many zeros it saw before. Okay, so the fundamental limitation of the finite state machine is it's only got internal states. It's got no external scratch paper. That's the intuition of what's going on here. That's why it's deficient. Okay, and so this suggests that this model, although it is very powerful, it can do all regular expressions. It cannot do something so simple as equality. Okay, so DFA is powerful. So all regular languages but cannot do equality. And since equality is such a simple problem to solve, or is such a simple task, this leaves us very disappointed. Okay, so it suggests that, this is not good enough for us. We need something that's more powerful, okay, if we're to do equality. And this is a general workflow whenever you're developing a model in any scenario. You're developing a model of computing for distributed. You're developing a model of computing for, mobile or low energy, or et cetera, et cetera. So you develop a model of computing. In our case, our computing model is beautiful because it's very easy to build. Finite state machine, easy to build. Okay, very powerful. But so we've understood its capabilities. Okay, but now we've understood its deficiency. And then you have to ask yourself, is this deficiency something we can live with or not? Okay, and we cannot live with a deficiency so glaring that we cannot solve equality. So we cannot live with this deficiency. Okay? And so we need something more. And then we may ask ourselves, well, what more do we need? Okay. And, this takes us back to the intuition I just mentioned, which is that the DFA has no external memory. So maybe can we develop a model of computing that has an external memory? So let's see what that might look like. So you have your, CPU. Remember that guy with the states, Q0, Q1, Q2, okay, up to Q maybe 7 or whatever, and it can rotate states. It's got its read head, which reads your input bits 1, 1, 0, 0, 0, 1. Okay, and this is the DFA, and then it has to say yes or no. Okay, but it has no external memory, so and since we need to remember something, and that something could be arbitrarily large, maybe we need an external memory. So what if we added an external memory? Okay, and the simplest kind of external memory is what we call a stack. Okay, so now we have added an external memory, which is a stack. Okay. And the DFA, in addition to being able to read bits and transition states, can also read, write, and pop from the stack. Okay. So how would it solve 0 to the n, 1 to the n? Let me just illustrate, and then you can read more about it in the text. Well, what it's going to do is, when it gets to its first 0, it moves into a state which says, I've got to my first 0, so let me start writing them onto the stack. So let's say I have the input 0 to the 5, 1 to the 5, let's consider 0 to the 5, 1 to the 5, and 0 to the 5, 1 to the 6. Okay. So I found my first 0, so I start writing each bit that I process, which is a 0, so I'm in a state for writing zeros, I write it to my stack. Okay, now the important thing about a stack is you only have access to the top. So you can write to the stack, you can read from the stack, and you can pull off the stack, so you can pop. But you don't have random access. Okay, so this is a very primitive form of external memory. So I've written my 5 zeros to the stack. Okay. Then I get to my first 1. So what do? I pop from the stack. Okay, and I transition to a new state which says I'm no longer writing zeros, I'm popping. Okay, I'm popping from the stack. Okay, because I'm as long as I get ones. So I keep getting ones, so I get a 1, I pop, the first one popped, the second one pops, the third, fourth, and fifth ones pop. Okay, and now I have no more bits, and so what I do, I check if my stack is empty. If so, there were an equal number of zeros and ones. If I get another 1 in my string, then I try to pop from an empty stack, and I immediately go to a reject state. Okay. If I'm processing ones and I get a 0, I can immediately go to the reject state, because then I've got zeros, ones followed by zeros. Okay. So this is just to illustrate to you how adding an external memory can allow us to solve that problem. Okay. Now, related to this notion of adding external memory, so we won't spend too much time on this type of a machine with this kind of a primitive external memory. This kind of a machine is sometimes called, this is called a deterministic push-down automaton. Push-down because it has a stack memory. Push-down automaton. Okay, so or a DPDA. Okay. It's not public display of affection. It's a push-down automaton. Okay, and we won't spend too much time on this because we have bigger fish to fry. Okay, but this is just to show you how if I allowed myself a little bit of extra, capability, i.e. an external memory, I can solve this equality problem. And now you should look at this and say, well, that's a totally different kind of a machine. Okay. Now, without this external memory, it's a simple machine, state transitioning machine that can read and then it has to output yes or no. So, easy to implement. Okay, what are your thoughts on being able to implement this guy? Interesting. Okay, so think about whether or not such a machine could be implemented. In the meanwhile, our next topic is going to be context-free languages, and mostly because we use them a lot in compilers and parsing and HTML parsers and so on and so forth. So it's a very important topic, but they are very related to these guys, to these deterministic push-down automata. Okay, they're very related to push-down automata, and the deterministic version, the one that I've shown you here, is one form of push-down automata. Okay, and so that's what we'll discuss next. But let's recap what we talked about today. So so far, okay, we talked about infinity, and infinity showed us that there are problems we cannot solve. Okay, period. Problems we cannot solve. Okay, because the set of programs is whatever program means. The set of programs is much smaller than the set of computing problems. Okay, and then we defined formally what is a computing problem, and that's a language, a set of finite binary strings. And then we talked about regular expressions, a powerful way to describe languages. And any regular expression can be solved by the computing machine that we introduced today, the Deterministic Finite Automata. So DFA solves all regular languages. It turns out that that's only the kinds of problems it can solve. Okay, and just like with infinity, we said there are problems we cannot solve. Today we actually caught one of those problems and put it on display with respect to the DFA. So we showed an explicit problem that we cannot solve when it comes to finite state machines. Okay, and that's a stunner. Well, first of all, it's a stunner that the finite state machine can solve all regular languages. Okay, such a simple machine. And then we showed that, it's not all powerful. There are things it cannot solve, simple things it cannot solve, embarrassingly simple things it cannot solve. Okay, and one way to address that deficiency is by adding memory. And so until next lecture, where we will discuss context-free grammars, checking out.